Looking at problem 4 from section 4.3. This is the word problem. It says an oil well off the Gulf Coast is leaking, with the leak spreading oil over the surface as a circle. At any time t in minutes after the beginning of the leak, the radius of the oil slick on the surface is r of t is equal to t squared. That's what we have here. It says let a of r equal pi r squared. This is just the area of a circle, okay, as we know. Pi r squared for the area of a circle with radius r. The first thing we want to do is find and interpret a of r of t. This is a composition of the two functions. So as we saw in the previous examples, we plug the radius into the area function. So I just take this radius function, plug it into the area function, as we see here. Just take the t squared, plug it in for the r there, and square that, so we get pi t to the fourth. So the interpretation of this is the area of the slick as a function of time. So what is this function going to be telling us? What is this composition going to tell us? It's going to tell us that at any given time, if we plug that t in again in minutes, that will tell us the area of this oil slick. So for example, if t is 1, we get pi times 1 to the fourth. That's just pi. If it's 2, then we get pi times 2 to the fourth power, so that'd be 16 pi, so it's just telling us the area at any given time. And of course, this function up here that we started with, this was telling us the radius of the circle at any time. Okay, so now we've got two functions, well, really three. This one is telling us the radius of the slick, this one is telling us the area of the slick, and this one was the one that connected the area and the radius. Okay, so then in part B, we're asked to find the derivative with respect to time. That's the d dt of this composition that we just saw here. So remember that the way that this works is we first take the derivative of what we call the outer function, that's the area function, with respect to its variable, that's r here. So that's dA dr, and then we multiply it by the derivative of the inner function, that's this one here, the r function, that's called dr dt. We'll do this in a sort of easier way in just a second. I just want to demonstrate the chain rule in action here. So dA dr, that's the derivative of a with respect to r. So that's just 2 pi r. So 2 pi r, that's dA dr. We multiply that by dr dt. That's the derivative of r with respect to time. So that's 2t. Okay, now really what we want this to be is a function of time. That's the d dt means we want this all to be in terms of t. So what we can do to make that happen is plug in what r is. R is equal to t squared from there. So we get t squared here. And then we still have this 2t. Now if we multiply all this out, we're going to get 4 pi t cubed. Okay, so 4 pi t cubed. Now notice that we could have just done this straight from here because we had that function a of r of t. This was already a function of time here. If I just did it that way, I would just put the 4 in front, 4 pi, and then lower that by 1, so 4 pi t to the third power. Of course, we have to get the same answer here. This is just sort of demonstrating what the chain rule is doing, but if you have that function, you can just jump right to the derivative here. Okay, the interpretation of this is the rate of change of the area with respect to time. Okay, so what that means is that, for example, after 1 minute, the rate of change would be 4 pi square feet per second. So it would be growing at a rate of 4 pi square feet per second when 1 second has passed. When 2 seconds have passed, then this would be like 2 to the third, that's 8 times 4, that's 32 pi. So that would be 32 pi square feet per second. It would be the rate that it's growing at 2 seconds. So this quantity here represents the derivative of this function composition. This gives the rate of change, the rate of growth really, the rate of change of the area of the slick at any time t. And really what we want to always remember about derivatives is that they always represent a rate of change. That's what a derivative is. So in this case, it's the rate of change of the area of this oil slick with respect to time.